Hey there, and welcome. Today, we are going down a rabbit hole on a classic brain teaser, one that really shows you just how weird and counterintuitive probability can be. It seems super simple on the surface, but it's a perfect example of why our gut feelings about chance, well, they're often just plain wrong.
Okay, so picture this. You walk into a party, it's pretty crowded, people are laughing, music's playing, it looks like any other get-together. But believe it or not, there's a fascinating mathematical secret just waiting to be discovered in this room. So, here it is. Here's the question. You're in a room with just 23 people. What do you think the odds are that at least two of them share the exact same birthday? Just take a second and make a guess. What's your gut tell you? Maybe 5%? 10%? It feels like it should be pretty low, right? Get ready for this. The answer is just over 50%. Yeah, I know. In a room of only 23 people, it's actually more likely than not that you'll find a birthday match. If your brain is kind of short-circuiting right now, you are definitely not alone. And that feeling of no way, that's exactly why this problem is so famous.
So, this is what's known as the birthday paradox. Now, it's not a real paradox, like a logical contradiction or anything. It gets its name because the real answer clashes so hard with what our intuition screams at us. So, let's pull back the curtain and figure out why our gut is so off the mark here.
Okay, so to really crack this thing open, we're going to need to grab a few tools from our mathematical toolkit. But don't worry, I promise we'll keep it simple and straightforward. First up, we've got the factorial. You see it with that exclamation mark. It's just a super simple way of figuring out how many different ways you can arrange a bunch of things. So if you've got 5 students, there are 5 factorial or 120 different ways you could line them up for a photo. It's a really powerful way to count arrangements. All right, tool number 2, permutations. This is all about counting arrangements too, but it's specifically for when you're picking a smaller group out of a bigger one. Think about picking the gold, silver, and bronze medal winners from a race. The order you pick them in is absolutely crucial. First is not the same as third. So this might look a little intense, but it's actually pretty simple. Think of N as your big pool of options. In our case, the 365 days in a year. And K is how many slots you need to fill, like the 23 people in the room. This formula just calculates all the different ways you can fill those slots without any repeats. Let's make this real and tie it back to our birthday problem. Imagine you're assigning birthdays to just 3 students, and they all have to be unique. Well, the first student has 365 days to choose from. The second can't have the same day, so they're down to 364 choices. And the third, they've only got 363 left. That's a permutation right there in action. And our last tool for today is the combination. Now, this is the flip side of permutations. A combination is when you're just choosing a group and the order is totally irrelevant. So a committee of Anne, Bob, and Chris is the exact same thing as a committee of Bob, Chris, and Anne. And here's the formula for that. You'll often hear people say N choose K. It's just for counting groups where order doesn't matter. Okay, so we've got factorials, permutations, and combinations. Our toolkit is ready to go. We are ready to solve this thing. Okay, here's where things get really, really cool. If you try to solve this problem head-on, it's a nightmare. It's incredibly complicated. So mathematicians found this super clever workaround, a kind of elegant detour that makes everything so much easier. I mean, just think about it for a second. At least one match could mean so many things. It can mean one pair of people shares a birthday. Or maybe there are 2 different pairs. Or maybe 3 people all share the same birthday. Trying to count all of those possibilities would just be a total mess. There has to be a better way, right? And this is the secret sauce. Instead of taking that messy, hard path, we're going to take the easy route. We're going to calculate the exact opposite of what we want. We're going to figure out the probability that nobody shares a birthday, that every single person in the room has a unique birthday. This whole trick works because of a basic, beautiful rule in probability. The chance that something does happen is just 1 minus the chance that it doesn't happen. So if we can figure out the odds that everyone's birthday is different, we just subtract that number from 1, and bam, we've got our answer. It's a game changer. Okay, the moment of truth. We've got our tools, we've got our strategy. Let's put all the pieces together and build this thing from the ground up. So first things first, we need to figure out the denominator of our fraction. That's just a fancy way of saying what are all the possible outcomes. For 23 people, each person could have one of 365 birthdays. So the total number of birthday combinations is 365 times 365 times 365, 23 times. It's 365 to the power of 23. It's an absolutely enormous number. Okay, now for the top of the fraction, the numerator. We need to know how many ways there are for all 23 people to have a different birthday. And hey, this is exactly what permutations are for. We're picking and arranging 23 unique birthdays out of 365 possible days. That's just p of 365, comma 23. And boom, here it is, the whole shebang in one elegant formula. The probability of a match is 1 minus the probability of no match, and that no match probability is the permutation we just talked about divided by that huge number of total possibilities. This little engine is what spits out that crazy 50.7% answer. Okay, so we've seen the mechanics, right? We've seen how the math works. But why? Why does it feel so wrong? The real secret isn't what you think it is. Just take a look at this curve. It's not a straight line at all, is it? It kind of creeps along at the beginning and then whoosh, it just skyrockets upwards. And you can see it crosses that 50% line right at 23 people. Once you get to about 50 or 60 people, a match is pretty much a sure thing. In this right here, this is the real reason. This is the secret. We've been thinking about the 23 people, but that's the wrong way to look at it. The real magic is in the number of unique pairs of people you can make. With just 23 people, there aren't 23 chances for a match. No, there are 253 unique pairs. Every single one of those pairs is another roll of the dice, another chance for a match. And that's why the probability explodes so quickly. All right, so let's do a quick flyby of what we've learned. We figured out the total number of ways birthdays could be listed. That was our denominator. We counted up just the lists where nobody shared a birthday, using permutations for our numerator. We used that super clever trick of solving for the opposite of what we wanted. And most importantly, we found the real reason for the surprise. It's not about the people. It's about the explosive growth in the number of pairs. You know, the birthday problem is more than just a cool party trick. It's an amazing reminder of how our intuition can totally lead us astray when it comes to probability. It really forces us to trust the math over our own gut feelings. And that leaves us with a pretty big question. If our brains can get something this simple so wrong, what other more important things in life are we getting wrong too?